Hello, everyone, and welcome to our inaugural session of our new NACE Calgary program platform. My name is Brett Johnson, and I'm the new program chair for the NACE Calgary, and I'll be your host for today's webinar. So obviously, with everything going on this year, looks a little different. We're not going to be hosting any in-house events, even if laws end up allowing us to do so over the next year. But instead, we're going to be running a bunch of webinars, and we hope to do it on a semi-regular frequency. We've got people lined up for a frequency of about every 2 to 3 weeks for the next little while here. In order to receive the latest updates on who's presenting and when they're presenting, please make sure to follow us NACE Calgary section on LinkedIn, as everything will be posted there immediately. We've also launched a YouTube channel as well, and that will feature each one of these presentations. So if you end up missing one, please be sure to check out there after a couple of days to see the video. We're also hosting this live on YouTube Live, so if Zoom doesn't end up being something that works out for you, please visit our channel and view the live sessions as well. Of course, all the information about this webinar and upcoming presentations and links to our YouTube channel can all be found on our website at nacecalgary.ca. So I'd now like to present Colin Scott. Colin Scott is a pipeline integrity engineer. He studied at Queen's and McMaster's University, earning a doctorate in materials engineering with a specialization in fracture mechanics. He consulted with the nuclear industry in Ontario before switching career focuses to primarily oil and gas and pipeline integrity. He's worked with D&V in Iowa, Enbridge in Edmonton, and Iris NDT here in Calgary. He is currently independent, but he's the host of an exciting YouTube series about similar topics to what he's going to talk to today. So Colin, we are absolutely excited to have you on our webinar today. Thanks again for agreeing to be with us and being the guinea pig for this whole new adventure we're going on.
Hello, Brett. Hello, everybody from NACEland here in Calgary. Thank you very much, Brett, for the invitation to join the session. I'm looking forward to presenting some work I've been doing recently, and I look forward to questions from the audience on some of the work that I've come up with. So let's go.
That's awesome, Colin. Do you want to tell us what you're going to talk about today?
Yes. I'm basically taking a second look at some of the corrosion assessments that we're doing. A lot of us are going to be very familiar with things like ASME B31G and DNV F101 when we do our corrosion assessments. But what I found a year or two ago is that when you look at the mathematical heart and soul of these equations, it's actually, I'll say, mathematically wonky, in that all of these equations are fundamentally based on length. And for a fracture mechanics perspective, they really should be based on depth. So in this presentation, to kickstart things, I kind of walk through some of the mathematics and walk through the arguments and logic that have kind of brought me to this situation. So I'm hoping it'll give people a chance to think about what we're doing in the industry, and hopefully refine little thinking and hopefully improve the way that we do things over the long run. So I'm looking forward to getting questions from the audience and see what they think of what I'm doing.
Thanks for that, Colin. None of this whole webinar and what we're doing here would be possible without our annual sponsors. Their contribution allows us to be able to provide this webinar series to everybody here at absolutely no charge. So today I'd like to highlight one of our gold sponsors, PipeTech. PipeTech has been a long-standing sponsor and supporter of NACE Calgary for decades. I can't remember an event that we've hosted or a conference without PipeTech being there. They've been very active in our industry, and their leadership has been active on our executive board as well. PipeTech brings a huge range of products and services, including a wide range of pigging solutions, pigging tracking solutions, and sealing products. To learn more about their products and services, or to watch Craig Ball imitate characters like Ron Burgundy or the Tiger King, please visit their website at pipetech.org. And of course, all our other sponsors are a huge reason why we can do what we do. Our sponsors have helped fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to the next generation of engineers. They do this by funding scholarships to students, putting on knowledge events at the university, and building a teachers camp program, which will bring in high school students to show them how to teach corrosion and materials in their classrooms. Each one of our sponsors We thank you for your continued support. So now Colin here has pre-recorded his presentation for you. So after recording, I'll host a Q&A session with Colin to answer any of your questions. If you have questions for Colin, there is a Q&A button within your Zoom software panel that will you can push to be able to write a question and then post a question. There is a chat log in there as well. If you post something in there, I might miss it because sometimes we get flooded with whatever anybody wants to have. So try and use the QA panel if you can. And for those listening on YouTube Live, if you have a question, please post in the comments and I'll try and read them as well. And so without further ado, here's Colin's presentation.
Hello, welcome to my pipeline integrity video that's titled A Closer Look at Corrosion Assessments in the Oil and Gas Industry. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, in Canada. Today I'm going to be talking to you about a corrosion assessment using the NG18 based equations. Some of you will probably know these equations better as the ASME B31G equations, or possibly the DNVGL F101 equations. The reason I'm calling them the NG18 based equations is because they were developed by the NG18 committee at the Battelle Institute in Columbus, Ohio, back in the late 1960s and the early 70s. This work was a seminal study in the pipeline integrity industry, and a lot of the work that was done back then, back 50 years ago, has evolved into the various models that we know today, including ASME B31G and DNV F101, as well as others. Now, those of you that have worked with these equations before will know that they're generally considered to be conservative. And in a way, that's a good thing because it means that the pipelines are safe. But if you're the one that's paying the bills on doing all the repairs, you might not be quite so pleased with that level of conservatism. For the last couple of years, I've been studying these equations, and I think I figured out why they're so conservative. So the goal of today is to share some thoughts with you on why they're conservative and what we can do about that, what it means, and perhaps how we can make some improvements to fixing the problems and coming up with more refined and accurate failure pressure predictions for our pipelines. Now, I should warn you up front that some of what I'm going to say here is a little controversial. So I'm going to ask you politely if you can try and keep an open mind, listen to what I have to say and think about things. And then later on, if you have any questions or you would like to debate any of my assumptions, I'm certainly open to having that conversation. So here's our basic NG18 equation, which many of you should be quite familiar with, ASME B31G. We have a remaining strength, which is defined as the predicted failure strength divided by the flow strength. And then we have a big fraction there, a big ratio. On top, we have 1 minus dt, where d over t is the flawed depth ratio with respect to wall thickness. And then on the bottom of that big fraction, we have 1 minus 1 over m d over t. So I'm hoping that a lot of you are quite familiar with that. You will notice that the equation has been stripped down. It doesn't have any shape factors in it or correction factors that you might be familiar with the ASME B31G equations. If you look at original B31G, you'll find that there's a 2/3 factor in there. If you look at the modified B31G, you'll find that there's a 0.85 factor in there. I've stripped this down just to keep things fairly simple. Now, the m that you see there is called the Folias factor. And the Folias factor is a function of a z parameter, and that z parameter is proportional to the length of the flaw squared divided by the diameter and the wall thickness. Now, if you look at ASME B31G or the other standards that use this form of equation, you'll see that there are different theoretical ways that you can do the Folias factor. But ultimately, that Folias factor it's a length-based factor. Now let's think about how we would typically do a model validation. Whenever you develop a model, you want to make sure that it's working properly, and that can be done through some fairly simple statistical means. So typically what you would do is you would go find some industry failure data. Now for me, I've done this as a paper study, so it really just means going to the library and seeing what I can find there, or talking to some industry colleagues. There's some of you out there that might work at laboratories in the industry, and you might be able to actually develop your own failure data by doing some hydro tests in the lab. Either way works. Now, what you would do is you would take that data and you would take the candidate model, in this case, the NG18 equation, and you would use that model to predict the failure strength of your corrosion flaw. Simple mathematical exercise. And then what you would do is you would compare the measured, the true failure strength, and you compare that to the predicted failure strength. And if your model is inherently correct, those numbers should match up pretty well. So let's do that. First of all, I've found some industry failure data. So I've got two data sets. One I'll call the Corrosion data. And this is from a doctoral thesis from the University of Waterloo from 2000. Thesis title is Assessment of Corrosion Defects in Pipelines by Dwayne Cronin. Now, if you look through that doctoral thesis, you'll find that he has 40 complete data sets where he's done some corrosion flaw testing in the lab. What's really good about this data set is that he has 23 full corrosion flaw profiles, which means that we can do a little bit of a refinement of our various calculations. If anybody's interested in trying to do an analysis like this, it's pretty easy to find that Cronin data online. If you just do a Google search on Dwayne Cronin and University of Waterloo, it pops up pretty quickly. So it gives you a good opportunity to take a look at some of the industry data and get a sense of how things play out. My second set of data I'll call the Battelle data, and that's from the Pipeline Research Committee of the American Gas Association, the 5th Symposium on Line Pipe Research, which was November of 1974. That's got 45 data sets. Unfortunately, that one's not quite so easy to find. I only have a paper copy. I'm sure there are a few paper copies floating around, but most of them are probably covered in dust and probably being used to prop open a few doors. Now, the Battelle data is the data that would have been used to validate the original NG18 equation. So that makes it very, very valuable. So let's go through that validation exercise. So here I have a plot where I have the predicted failure strength on the y-axis, and I have the true measured failure strength on the x-axis. And all those red circled data points represent my 85 data sets. Now, what you'll see is most of those data points are below the diagonal that runs across this plot. That means that in general, the model is quite conservative. You'll see that there are, I guess, 4 data points above the diagonal line, and these represent non-conservative predictions. So those would represent unsafe predictions for the pipeline. But the great majority of all our data is below the line, meaning that it's overly conservative. Now, being overly conservative is good in that it means that we are ensuring pipeline safety. But if you're the one that's paying the bills on doing all the repairs, this could well give you quite a bit of heartache. You'll see that there are quite a few data points that are quite low down on the plot there, meaning that there are a lot of repairs that are potentially being done that are quite unnecessary. When you look at the trend line that I've put through there, y equals 0.75x, you get a sense of just how much conservatism there is in this model. Now, some of you will like the idea of conservatism because it ensures safety. What concerns me about this, though, is that if we have some conservatism in the model and we don't have a good explanation for it, we really do have to question the mathematics behind the underlying model. And if we have a question about the underlying mathematics of the model, then we have to really question some of our probabilistic calculations that are being done in support of our pipeline integrity program, and we have to really question some of the reliability numbers that we've got coming out of our integrity program. So my goal here is to try and come up with a model which has got a lot better accuracy. Now, this plot shows you that we've got over conservatism, but it really does not give us a sense at all of why we have that conservatism. So that's what I'm going to show you today that I think is really interesting, and it might catch some of you by surprise a little bit. Here's what I call my atypical model validation. It starts the same way. I go and find some industry failure data, but the next step takes a bit of a turn. I use that data and I use my candidate model, in this case, the NG18 equation, and I use it to back calculate what would be the effective Folias factor that was necessary in order to make the model work perfectly, right? So I essentially take the NG18 equation and I kind of turn it inside out. And rather than solving for the failure strength, I'm actually solving for the Folias factor. And I could do that because I already know what the failure strength is from the lab test or the surface failure. Now, if I compare that back calculated effective Folias factor to the theoretical Folias factor, so by that I mean compare it back to the equation that you'll get in ASME B31G, those numbers should line up pretty well, shouldn't they? And if they do, then I know that the mathematical formula that's underlying the model is pretty good. So let's do that. So here's my basic NG18 equation again, but I've actually turned it inside out. Before I'd solved for the predicted failure strength divided by the flow strength, but in this case, I'm looking at the actual true failure strength built into that equation. And as you can see, I'm calculating the effective Folias factor. It's a little bit tricky to wrap your head around this equation. I basically had to pull out my pencil and go through the exercise, and this is how things play out. Now, what's interesting with this is just from a mathematical perspective, this is really kind of an unusual looking fraction. So it's got me a little bit suspicious just to start with. Let's see how it plots up. Okay, so here we have a plot where we have the Folias factor on the x-axis, and we have that flaw length parameter z on the y-axis. So as you go from left to right on this plot, you're looking at longer and longer corrosion flaws. Now, you'll see that I've plotted a solid red line, which represents the Folias factor, and that's basically the equation that you get out of ASME B31G. In this particular case, I've used the modified B31G Folias factor. If you were to try this with any other Folias factor, you would get a slightly different curve there. Now you'll see with the red circles, these are the back calculated effective Folias factors that come out of those 85 data points that we just looked at a couple of minutes ago. Now, if the mathematics behind the NG18 equation were fundamentally correct, we would expect all those red circles to fall along that curved line. They don't. So I find that to be a big, big surprise. I would not expect the data points to follow the curve perfectly. I would expect there to be some just natural scatter in the data. But quite frankly, this is really not a good correlation. You see that all of those effective Folias factors fall along a fairly horizontal line there between 1 and about 1.5. And you can see that I've got a dashed red line, a trend line through there, through all of those data points that shows effectively a zero slope. Now, this becomes very important to integrity programs, because what this means is as you go from left to right along this plot, you've got longer and longer flaws. And those longer and longer flaws are increasingly farther and farther away from the theoretical Folias factor. Right? So that means that as your flaws get longer and longer and longer, you're actually getting more and more and more conservative in your prediction if you're using that NG18 equation. Now, I think that for those of you out there that are pipeline operators, this should be giving you a little bit of heartache. I'm assuming that there are times where you send an inline inspection tool down the line, you look at all the flaws that that tool reports, and you do a failure pressure calculation for each one of the flaws, and then you would come up with a dig list. What's really a tricky thing to work around here is that if you find a very long flaw, you know from this plot that that long flaw will have an overly conservative failure pressure prediction. Now, if you do the calculation and it shows you that that flaw should be on your dig list, you're going to be tempted to run out and do a repair, and that repair might cost you $100,000 to go and dig up the pipe. But this plot tells you that the prediction for that particular long flaw is potentially very, very overly conservative, in which case maybe you don't need to go and dig it up. So unfortunately for the pipeline operators, I think that this is going to lead to a little bit of head scratching. This particular plot puts some uncertainty into the pipeline integrity programs that some of you work with. Now, typically, we would make the natural assumption that longer flaws have lower failure strengths. I mean, it just seems intuitive. It seems typical. But it's easy enough to check that out. So here I have a plot of the remaining strength. And so that's the failure strength from the 85 data points divided by their flow strengths. And I've plotted that against the flaw length. In this case, I've got millimeters. So as you go from left to right on this plot, you're actually going from shorter flaws to longer and longer flaws. Now you'll see that there really is not a strong correlation there. I do have a trend line there with the blue dashed line. And you can see that going from a 0 length flaw to a 1 meter flaw, you lose about 10% of your remaining strength. That's really not very much. So that's demonstrating that you really do not have a strong susceptibility to flaw length when it comes to the failure strength calculations. You'll see that I've got an R squared value there of 0.04. Now that's really not a strong correlation. That really tells us that that trend line is somewhat meaningless when it comes to how much does length affect the remaining strength. There is a little bit there, but really not as much as the Folias factor approach seems to be implying. So let's get back to the Folias factor and think about that a little bit more. The Folias factor was originally derived to calculate the stress concentration associated with the length tip of a through-wall crack and to determine if it might extend axially and rupture. So that Folias factor is a very, very important part of through-wall crack assessments, which would be used for a leak rupture boundary. And with a leak rupture boundary, you're worried about a short crack that's extending and getting longer, that's extending in the axial direction. I guess if we flip this thing on its head, what's more important is that the Folias factor was not derived to calculate the stress concentration associated with the depth tip of a flaw, either corrosion or crack. And it was not developed in order to determine if that flaw might extend radially and cause a failure. So that's a very, very important thing. We have a factor here that's buried into our NG18 equation, which is derived mathematically and theoretically based on length. But we're not worried about our corrosion flaw getting longer. We're worried about our corrosion flaw getting deeper. So that brings up a very important thing. Direction. When it comes to a corrosion flaw failing, we're worried about it getting deeper. But when we look at the mathematics of the NG18 equation, we have a Folias factor in there, which is mathematically and theoretically all about a flaw getting longer. So that makes me scratch my head a little bit. When we think about why the NG18 equation is conservative, it's because the mathematical weighting of the equation is, in my mind, too heavily focused on length and maybe not so much against depth. Now, if we look at the various industry models, you'll find that there are several industry standards out there that use this basic equation. Before I've mentioned ASME B31G and I mentioned DNV F101, which is, these are the standards that I'm guessing a lot of you will be more familiar with. When it comes to ASME B31G, we have both the original version and the modified version. And then if we want to go to a level 2 assessment, we can go to more complicated things like R-string or P squared. We can go to API 579, which has got a chapter or 2 or 3 chapters on corrosion assessments. They use a very similar technique in there. We can go to British Standard 7910 and have a similar technique. Now, all of these industry models include some mathematical form of the NG18 equation, but they're using them for surface flaws as opposed to through-wall flaws. So I scratch my head a little bit here and I wonder, is that really 100% appropriate? Now, I'm guessing that there are some viewers out there that are going to point out that the original and modified ASME B31G equations are known to be overly conservative, and that's why R-string was developed. And R-string is certainly an improvement over the basic B31G. Now, the thing with R-string is you're going through a full profile, you're looking at multiple length and depth combinations of the full flaw profile, and you're selecting the lower bound of those various combinations and permutations. And that seems to be a good idea, but if you stop and think about it, you are actually, by going through that algorithm, you are actually removing length from your assessment. when you do your R-strain calculation, you're typically going to end up with a shorter flaw than you started with. Now, my argument would be that by taking length out of the calculation, you're essentially taking out error that's associated with the basic NG18 methodology. If you look at the validation that's been done on R-string, you'll find that that's about 30% overly conservative. And those are not my numbers. The 30% conservatism is reported by Corrosion in his original thesis. And that R-string conservatism of 30% is also reported in a recent PRCI report. Now, that recent PRCI report also came up with a refinement of R-string, which is called p-squared. When you look at p-squared has a reported conservatism of 13%. So that p-squared really is a step in the right direction, I think, but it's still based on that underlying NG18 equation. And so it still captures some of the over-conservatism associated with the basic model. So let's think about this. We have an NG18 equation that's been used for about 50 years. When you work that equation backwards, you find that the theoretical Folias factor does not match up with the back calculated Folias factor. And that seems like a problem. And then if you plot the remaining strengths as a function of length, you'll see that there really is not a strong correlation between strength and length. So that's a bit of a head scratcher. And then when you go and take a look at the theory behind the Folias factor, you come to realize that that is theoretically and mathematically based on length rather than depth. So when I started to do this original study a little while back, I really ended up scratching my head a lot trying to understand what we can do to fix this. What I ended up doing is going back to the original NG18 work that was done 50 years ago, and I recognized that there was a strong focus on length. And I decided to turn the tables a little bit and rederive some of that work, specifically their crack model work, and do it from the perspective of depth as being the focus rather than length. And what I ended up doing is developing something I call the gamma exponent model, or nicknamed the GEM. Now, it can be used for both corrosion and cracking. The cracking model is a little bit more complicated. It's very, very simplistic. So here, I'll show you that. So here's the gamma exponent model. And this is specific for localized metal loss. This is not to be used for cracking, and this is not to be used for uniform wall thinning. Now I have a remaining strength, which is equal to the predicted failure strength over the flow strength. And that's equal to 1 minus dt, just like we saw before. But here we have an exponent on that of gamma. And gamma is equal to the minimum of the length of the corrosion flaw divided by the radius, and up to a maximum of 1/2. Now, a lot of you will look at this and think that it's just a simple empirical model where I took the remaining ligaments, basically pulled that out of the air, whacked an exponent on it, and it seemed to work. It's not quite as simple as that. I've actually gone through a rigorous theoretical derivation based on blunt flaw analysis. When I look at my cracks and look at the depth considerations of a crack, and then I consider how things change for blunt flaws, I actually managed to derive this. So it's not just pulled out of the air. There is a derivation behind it, but it's a little bit complicated to explain to you in this video. I do have an ASME journal paper that would explain that for those people that are interested in the mathematics. Now, one thing that's going to give a few people heartache is that if you look at that gamma exponent, it is limited to 1/2. And that means that the remaining strength, as a corrosion flaw gets longer, is actually limited to the square root of the remaining ligament. And I'm pretty sure that that's going to cause a lot of you some real heartache, because that's not intuitive. I will tell you that that half exponent does come out of the mathematical derivation, and I do have a technical rationale for it. We'll bounce back to that in a couple more slides. Now here's the fine print on the model. All models have fine print. First is that the flaw depth can be modified by a pi/4 factor in order to approximate a semi-elliptical profile. But that's pretty standard in the fractal mechanics business. It's used for both cracking and corrosion. Ideally, you have a full flaw profile and you can come up with something a little bit more accurate, but it's a fairly reasonable approximation to call your corrosion flaw semi-elliptical. Now, if you do have a full flaw profile, I have also developed a level 2 algorithm. So it's a little bit like R-string, but there are a couple of key differences. And my ELM algorithm can be used for a more refined prediction. I'm not going to tell you all the details of how that works right now, but I will tell you the results of how well that ELM algorithm does when I use it on the full flaw profile. The flow strength I've used for all the validation is yield strength plus 69 megapascals or 10 KSI. That's pretty standard. I did not mess around with any of the other variations. My derivation is essentially a flat plate solution, and so because of that, I'm limiting to thin walled pipe. I've come up with an arbitrary d over t of greater than 20, and that's somewhat arbitrary, but it seems to be working. As I mentioned, the gamma exponent limit for the metal loss calculation is 1/2. Now, that's going to worry a few of you, so I'd like to show you a quick demonstration that's actually, I think, legitimate for my data set anyway. So before we took a plot of the remaining strength as a function of length, this time we're going to do a remaining strength as a function of the flaw depth ratio. So there you see y-axis has got remaining strength, x-axis has the flaw depth ratio. We have those blue squares that represent all of my 85 data points. Now, hypothetically speaking, if you were using the basic NG18 equation, if you go through all the rigmarole of the math and you consider a long flaw, what does your mathematics converge to? You would expect your remaining strengths to converge to that red diagonal line. However, with my GEM model, I've demonstrated in my journal article that the more reasonable limit to that is 1/2. So that means that the green dashed line, which represents the square root of the remaining ligament, becomes the lower bound limit. Now, what's interesting here is that all of my data points are above that green dashed line. So I think that this is pretty good evidence for this data set anyway, that gamma exponent limit of 1/2 is pretty good. If that GEM limit of 1/2, if the gamma exponent limit of 1/2 was not correct, you would expect to see a lot more of those data points lying much closer to that red dashed line. The fact that there aren't any in that sort of envelope zone means that the square root relationship seems to be pretty good. Now, what's important here is the gap between the red dashed line and the green dashed line represents over-conservatism in the NG18 equation. And that represents a lot of money being spent by the pipeline operators, perhaps unnecessarily. Now here, if I take the basic GEM model and put my 85 data points, I can do a simple validation, just like we saw before. Here I've got the GEM predicted failure strength on the y-axis, and I've got the true measured failure strength on the x-axis. And in this case, I've included a pi/4 factor to simulate a semi-elliptical flaw. You'll see that the data points line up fairly well. There are a few more data points over the line and represent non-conservative predictions, and there are some data points that are underneath the line and represent overly conservative predictions. But these data points are bunched a lot closer to the diagonal, meaning that the model itself is inherently more accurate. When I put the trend line through there, y equals 0.92, I find that my model is going to be about 8% overly conservative. As I mentioned before, my goal here is to come up with an accurate model which will convince me that the mathematics behind my model is correct. And so this seems to be a step in the right direction. Now, at this point, I still don't have great precision. And in order to improve the precision, I have to look at my level 2 ELM algorithm that I've developed for those 23 full flaw profiles. When I do that, I can improve things quite a bit. Again, we have the predicted failure strength on the y-axis, the true measured failure strength on the x-axis. And here, my data points seem to line up a lot better with the theoretical line. Y equals 0.98 means that I've got about a 2% over conservatism in that model. Now, I only have 23 data points to look at, but quite frankly, I think that this is really a step in the right direction. If you were to compare this to, say, R-string calculations, the R-strength calculations would be about 30% overly conservative. And if you compare it to the p-squared model that was recently developed by PRCI, you would find that that's about 13% overly conservative. So things seem to be lining up, I think, fairly well here. I can do some simple statistics. So for the basic GEM model, assuming the semi-elliptical flaw shape, I have an accuracy estimated at 1.09. And so that accuracy, I mean the mean of the failure ratios, where the failure ratio is defined as the true failure strength divided by the predictive failure strength. And if I take a standard deviation of all those failure ratios, I find a precision of about 18%. So that looks pretty good. If I look at the level 2 ELM algorithm I've developed and look at the full flaw profiles, I can improve that accuracy to 1.01 with a precision of 8%. So it seems to me that that's a step in the right direction. Now, I should mention that a lot of you, I'm sure, are skeptical of that square root relationship. But it seems to me from these statistics that it seems to be working at this point. I would certainly love to have some more data to play with to really confirm this and lock it down. But at this point, that square root relationship seems to be working fairly well. If you're interested in this type of work, I do have 3 real publications, 1 through NACE and 2 through ASME. For those of you that are interested in the mathematical derivation of my GEM model, take a look at ASME Journal of Pressure Vessel Technology. I'll tell you that that is really not an easy read because it's full of math and theory and stuff that will confuse all sorts of people, including myself. If anybody's interested in further viewing, I do have some other YouTube videos. One series is called Pipeline Integrity, Things That Make Me Go, And that's basically a summary of what you've seen here today, but also extended into the cracking world. And then I've got a second series called the Gamma Exponent Model Validation, where I take a look at my Gamma Exponent model and I show the statistical validation work with several other flaw types: corrosion, cracking, stress corrosion cracking, circumferential cracking, and through wall crack assessment. So please dig around for those if you're interested. For those of you that have made it this far, thank you very much for your attention. I hope I've given you a few things to think about. I know that some of the things I've said here are going to come across as controversial because they don't seem to be intuitive. I've checked my math. I encourage you to dig up these data sets and try it for yourself. I'm certainly open to conversations about other data sets and how the theory fits in with what we're doing in the world of the pipeline integrity. Thank you very much for your time, and until next time, have a good day.
Awesome, Colin. Thank you so much for doing that. So we have the Q&A line has been open this entire time. Please be sure to enter your questions in there and I can help read them off. So just to start things off. So Colin, what was the inspiration for you to, dive into all this work that you laid out in the presentation? Why did you want to suddenly rock the boat on the Folias factor?
I think this was a couple of years ago. I was involved in a consulting project where I was looking at various models that could be used for the pipeline operators. And when you look at the various models, you've got things like API 579, which means that you have to dig through a 1,000-page manual to figure out what the heck is going on, and that's not particularly easy. The other option is you can go with Corlas, and up until recently, there was a period where Corlas was not available commercially, so that wasn't really an option. And then when you look at things like the original log secant model or the modified log secant model, those ones are considered dated. So anybody in the fracture mechanics world that's using those for their pipeline operators is going to be considered to be not really up to standard. So I ended up, I guess, taking a look at the original modified log secant models from the cracking perspective. And as I looked really hard at them, I looked at how they were derived, I recognized that all the derivation is based on length, which from a fracture mechanics perspective just doesn't make a lot of sense. You're not worried about your cracks getting longer, you're worried about your cracks getting deeper. So as I sort of dug around in all the mathematics, I came to realize that I think those original models came together and they were used for both cracking and corrosion. And for a couple of reasons, they kind of sort of worked. I mean, if you develop a model and you say to yourself, the original log secant model for cracks is about 10 or 15% off, you'd say to yourself, okay, I'm going down the right road. And if you look at the B31G, it's 30% conservative, which is a bit more, but you still think that you're kind of sort of on the right track. And my suspicion is that people thought that they were close enough to the truth that they sort of, they didn't stop to have a good think about that Folias factor length depth issue. And the more I looked at it, the more I thought about it, the more I thought this could be the reason that everything is coming across so conservative. So I went back to the drawing board and re-derived everything from a depth perspective. And if you see these numbers that I just showed you, it seems like things are pushed towards the unity line a lot better. And the same works for my cracking work. So I like to think that I'm kind of like fixing a mistake that's just buried deep, deep down inside that nobody quite recognized because it wasn't an obvious enough mistake to throw all the numbers off. So there you go.
Awesome. Thanks, Colin. Appreciate that. So I was curious, the predicted failure strength slide looked that it showed almost as much data above and below the line. I'm curious, how is this conservative? And
sorry,
maybe I should show that slide here. Let me just play with this to get that.
If you're talking about the
just do Google the underlying model.
Okay, that one, what you see there is the trend line that's at 0.75. So 0.75 is less than 1. What you can't see there is there's actually a dashed gray line that's at unity, that's an exact diagonal. And for some reason, be it the video or somehow with Zoom, that gray dashed line is actually not showing up very well. So you'll have to trust me that the 0.75 line is actually substantially below what would be the y equals 1x line. I'm sorry, I didn't realize that that line was going to show up so faint there.
It may be just because it's on a small screen. I think it looked clearer when it was blown up. So
yeah, yeah. When you look at that, there is a gray dashed line. I think it shows up a little better on my YouTube channel, and you see that there are 4 or 5 of those circles that are above the unity line, and then the other 80 are below the unity line. So that's where you've got that sort of 80 versus 5 over conservatism.
Awesome. So what are the next steps based on this video that we would need to make some industry-wide changes based off of your theories?
Well, what I'm trying to do here is I'm trying to spread the word and sort of open up the conversation. I started doing this about a year or 2 ago, and I've had conversations with various people. It's very difficult to get traction on a new model, though. I think everybody's super busy and everybody's sort of set in their ways. The pipeline operators, they have a standard to follow, they have regulations to follow. They're kind of too busy to do things. What I'm trying to do here is I'm trying to sort of share the conversation. Hopefully people will look at what I've done and have a good think and say to themselves, look, length and depth are fundamentally different things. I mean, we have to get those in the right spot. I mean, we're looking after billions of dollars worth of assets, and we should be doing that technically right. The people that are the pipeline operators, if they're going to have a look at this, they're probably going to say to themselves, having a model that is 30% overly conservative through B31G is potentially costing some of the larger operators $100 million or $200 million. And so if those pipeline operators are fine with spending that money unnecessarily, they can go for it, but I don't think that they will be. So what I'm trying to do is I'm trying to promote the conversation, get people thinking about theory, get people thinking about how they can refine their assessments and not do unnecessary digs. And I think for me, what it comes down to is this conversation has to land on the lap of some senior people within the industry that are interested in doing things technically correctly, are interested in sort of refining things for the pipeline industry to make everything work a lot better. And importantly, those senior people have to have some influence in the industry in whatever way, shape, or form. And those people could be regulators who ask the question of their pipeline operators, hey, let's talk about the math here. This could be the pipeline operators who talk to their engineers, the senior people talk to their engineers and say, look, if there's a way that we can be not digging up pipe that doesn't need to be dug up, then we need to do some internal studies. This could come down to groups like PRCI and SEPA saying, hey, this is potentially a big change for the industry. Let's put together a group, or let's put together some funding to basically validate what I've done and see if the industry as a group wants to move forward on it. Part of the reason that I put out the YouTube videos is basically to challenge other people in the industry to look at that Cronin data set, which they can find online, look at the equations. And I think anybody that's sitting on this video is going to be quite capable of finding that data set and playing with Excel for an hour or two and confirming what I've done. If somebody finds a showstopper that doesn't work, please let me know and we can talk about it and you know, I can fix up any problems. But I really want to essentially crowdsource the validation of this to get people on board with what I'm doing, and then that hopefully will gain a little bit of momentum towards the regulators and towards the consultants and towards the PRCIs and operators of the world that can do something.
Fair. It sounds potentially promising on that for sure. And certainly I think a lot of us are thinking, well, looks great, but I mean, how would a regulator ever agree to that? So
that's something that I can jump in on. If you're in Canada and you're working to the regulations, you're probably using CSA Z662. And Z662 will tell you that thou shalt use the 85DL method, which is the modified ASME B31G method, or thou shalt use the effective area method per, you know, PRCI report, whatever. So that's essentially our string. But if you dig around really deeply in the CSA Z662, there's actually a clause which says any other models that you know, are being considered for an assessment can be used, but then they would have to specifically be approved by a regulator. So Z662 kind of gives you a little bit of a back door that you can slide out of, and quite frankly, anybody in town can find that Cronin data or whatever other data they've got, put together a spreadsheet, and put together a pretty clear argument for the regulator that you're actually improving some accuracy here. So that's one thing. If you're down in the United States, the Code of Federal Regulations says thou shalt use ASME B31G. But within B31G, there's actually a clause that says you are not limited to the models in this standard. You can use any model you want, provided it can be demonstrated to be a reliable model at predicting corrosion failures. So again, that's kind of a back door that you could potentially go to PHMSA and say, here's the Cronin data, here's some other data, here's the math, here's the spreadsheet, we've checked this, we've checked that, we've got an improvement in accuracy, what do you say? So there are a few little, you know, there are some options, but ultimately it's going to come down to you know, doing a thorough study and convincing the regulator that the mathematics is legitimate and you're not going to cause any further problems by pushing things in completely the wrong direction.
Fair enough. Good point. Can you comment about the conservatism within the effective area calculation? Like, do we find that generally it's removed, or is there still a lot of conservatism if you use effective area to, like, R string, for instance?
Well, the effective area or the R string, based on the recent PRCI study that was, I think, was done primarily by the folks at TransCanada, their mathematics showed that they had about 30% overlay conservatism, which is quite a lot. And, you know, my argument that comes down to is, even though you've got the level 2 algorithm, and even though you're looking at effective areas and you're reducing the length on your flaw, you still have that NG18 equation that's just buried deep down there that will always kind of rear its ugly head and always give you some extra conservatism that is very likely unnecessary for a lot of flaws. I think that the p-squared algorithm that was done, I think, was a really good refinement of R string. But again, it still has that NG18 equation sort of buried deep down inside. And even the p-squared model, which is a really, really great pencil sharpening, it still comes out at about 13% overly conservative. So that's why I keep arguing that underlying mathematics that's what's pushing everything towards the operator spending more money than they need to. My goal here was to come up with a model that would sort of follow along that unity line. If you've got accuracy, then you can apply your conservatisms like you usually would. Then you can say lower bound yield strength. Then you can say we're going to add a tool tolerance. Then you can add on all the usual stuff, but know that you've got a good starting point with an accurate model.
Interesting, because I know like a lot of operators are looking at p-squared and saying, yep, this is kind of the next revolutionary step in assessment, but are a little bit reluctant to even move towards that. So it's a great comment on that by saying that even that, there's still some conservatism and there's still too much length component on it. And
I think that one of the other concerns with a p-squared might also be that the algorithm is a fairly complicated algorithm, right? So it's a little bit like R-string in that you're looking at lengths and depth combinations, but then you're also looking, the plausible profiles means that you're only looking at a limited combination and permutation of paths of corrosion. That's going to make things it's going to make things mathematically a little bit more complicated, and the more complication you put into the assessments, the more opportunity you have for something to kind of get missed and slip up and go sideways. So there might be some of that too. I know that whenever I come across something like API 579, it's a 1,000-page document. And if you accidentally pick the wrong number out of that monster table, everything's going to go sideways, but you might not know it. So I'm a believer in the keep it simple, stupid philosophy. And I think the one thing about the gem that's helpful is that it's very simple, and I think less room for error than some of the other models.
Fair enough. Awesome. So on the statistical side of things, maybe just a clarification, you mentioned that you generally have accuracy measured like 1.09 and 1.01. How do you, like, does this imply how close it's to 100%? Maybe you can just clarify that.
Well, essentially, when I figure out the accuracies, what I'm doing is I'm taking the true failure strength. So that's what was measured in the lab or measured during a service accident. And then I'm looking at what what's predicted by the model. And I'll do that for every one of the data points. So each one of those data points, you would hope would have a ratio between the true and the predicted of around 1, meaning that was approximately accurate. But it turns out that's not the case. If I find that ratio is substantially below 1, then that represents an overly conservative prediction, which means potentially doing a repair that's really not necessary. However, if things go in the wrong direction, let me stop and clarify. I'm confusing myself because my plots go in a different direction than the statistics go. If I'm on the plots and I'm below the line, that's conservative. If I'm looking at those failure ratios and I'm above 1, that's conservative. My apologies, I got ahead of myself. So the further you are away from 1, the further you are conservative or non-conservative. Sorry, I had the image of the plot in my head and I was thinking lower is better, but then your statistics, I've defined it the other way around. My apologies if I've confused anybody there.
No worries. Thanks for the clarification on that. That kind of makes a good picture on it. So what's your thoughts between kind of the, difference between or interplay between ILI accuracy and model conservatism? ILI accuracy is plus or minus 10%, 80% of the time. All these models are different conservatism. Most of the reason why a lot of operators widely adopt these conservative algorithms because they are worried that ILI features may be significantly deeper than originally intended. So having, like, for example, looking at that graph and saying, okay, yeah, it's great, all the burst pressures are way below my estimated or calculated burst pressure is good, way higher than that, because that's conservatism on it. But obviously with your model, that would remove all that. What's your thoughts between them?
Yeah, I fully expect to get the argument that people will come up with and they'll say, well, the model is conservative, therefore it kind of sort of doesn't matter if it's wrong. Conservatism and safety is obviously our priority as engineers, but it's really only half of our job as engineers. As engineers, we have to look at safety first, but particularly the pipeline operators have an obligation to look at being financially responsible. And then as professionals, we also have an obligation to do things that are mathematically correct and mathematically defendable. So, you know, my argument is, yes, if you want to just say these models are safe, therefore we're good, that's fine, but you're really only doing half the job. And the conservatism that you've got built in there, or you think you've got built in there, it really doesn't have an explanation until now. So that basically means you've got conservatism built into your model that is a big question mark in all of your reliability calculations, all of your probabilistic calculations, all your everything. My feeling is by moving towards a more accurate model, you've taken out one big question mark out of your assessment, because you can, because the mathematics demonstrates that you can. When you have an ILI vendor, and like you said, they will typically say they have a plus or minus 1 millimeter depth sizing 80% of the time. That's the best that they can do, given that they're working with sound bouncing around in a pipe. Like there's only so much you can sharpen your pencil there. So I think it's reasonable to say to yourself, we know that the ILI's got some uncertainty, and therefore we're going to add an extra tool tolerance to our calculation. If you're doing a crack assessment, you would say to yourself, well, I'm going to use a lower bound toughness because I don't know what the toughness is, or I'm going to use a lower bound yield strength because I don't know what the yield strength is. But if you have a model that's accurate and a model that's inaccurate, which one do you take? Do you take the one that has a big question mark over it because it's safer? Or do you say to yourself, we have enough knowledge now and we have a mathematical basis for using that more accurate model, and we can make up for conservatism in other ways, shapes, and forms, using lower bound yield strength, lower bound toughness, look at the pressure profile across the line, all that kind of stuff. I'm trying to remove a question mark.
Fair enough. No, thanks. I appreciate that. We have time for just one more question here before we're out here. So I know there's a few more questions in the chat. Maybe Colin, if you don't mind, maybe after doing this, maybe just kind of typing out a quick response to them. Sure. If the session doesn't totally drop out here when we end this, but
if the session doesn't crash, I will jump into chat. If the session does crash, anybody that's watching, if you want to find me on LinkedIn, you can find me and just send me a question through there. I'm glad to answer things, because I'm sure that people will kind of sleep on this and they'll think of something that they didn't think of before. So LinkedIn works for me.
Yeah, and I know it can be hard to be able to get your thoughts down on a piece of paper in time and send it off before the webinar ends. So totally fair. So last question here. So usually as flaws propagate lengthwise, there's often an assumption that they will then increase in depth too. It's often quite observed as well. So do you consider the probability of correlation to be a factor when this whole full length component is being done? And is that a good indicator?
If we're looking at corrosion flaws, it's completely reasonable to say that these, as corrosion occurs, your flaws will get longer and deeper. I agree with that. What I found in my study, though, is once you get longer than a certain value, it really kind of sort of doesn't matter anymore, and really depth is the only factor. So when you look at my gamma exponent, I say it's the minimum of length divided by the radius up to a maximum of 1/2. Okay, so what that essentially means is if your corrosion flaw is any longer than 1/4 of the diameter of the pipe, it doesn't matter if it's 10 meters long or 20 meters long. You're not ultimately changing what the failure pressure is going to be. And that's going to be something that's going to give a few people a little bit of heartache. Again, it comes back to my ASME journal paper, where I demonstrate where that value of 1/2 comes from. It does have a rationale to it, though it's a little bit complicated to explain here. Yes, as your corrosion flaw gets longer and longer, you will be reducing the failure pressure until you get to past about 1/4 of the diameter, and then it's really not going to make a whole heck of a lot of difference. It's a little bit different for cracking, but that's the gist of it.
Fair enough. Awesome. Well, fortunately, everybody, we're all here out of time. Thanks again, Colin, for your great presentation and for all the great questions that you answered. So to everybody still left on the line here, we do have actually our next 3 sessions all booked up. We can, on Friday the 13th, we have Artie and Burke from D&V. They will be doing a presentation on engineering assessments. If you guys recall, just before pandemic hit, they were going to do a live session for us at the Petroleum Club, and we had to cancel that the day before. So they'll be redoing that on the 13th. We've got Sankara on the 27th, and Dr. Frank Chain on December 11th. So please be sure to keep tabs on our LinkedIn site, and we'll be sending you blasts for that out on when to register for that. So if you yourself are interested in sharing your research or your experience or an interesting case study that you're doing and you'd like to share on our platform, please email me at program@nasecalgary.com, and we'll be able to make that happen. There you go. There's the email address. So thank you everybody for joining today. I hope this was informative and helpful, and we'll see everybody in about 2 weeks. So thanks again, and stay safe out there.